All right, good afternoon, everyone. We are going to get started here. Wanted to talk briefly about the end of last class. I was talking to you about that fiber optic problem. And if you go back and look at the video for this, I stopped here when we had found the cost function. We had taken the derivative of the cost function and we still had to set it equal to 0. And I thought about doing this in class today, but it would take about 10 minutes. I didn't want to do it. So I made a video of me solving that equation and I put it in our YouTube playlist for the class, and it's called like fiber optic something or another. Just look for it. I just uploaded it today. If you want to see me solve that equation and get the critical numbers, then go watch that video. And that'll give us like the final solution for that problem. We'll be officially done with the fiber optic problem. Okay, so that's, just want to point that out to you. And then today we're gonna do more of what we did last time. I only did like 1 or 2 examples, so I'm gonna do 3 more examples from 4.1 because I know the homework was probably like, whoa, what's going on? So I'm gonna do a couple of problems. And oh wait, hold on, this is the wrong day. I'm gonna do more of this, and then I'm gonna do mean value theorem, and that should be pretty quick. And then we're going to get into 4.3. Hopefully just start it, and then next class we'll actually finish 4.3. All right, so let's get down to business. So the main idea from last class was that from 4.1 was we had this new thing called the closed interval method. And it was the method that we used to try and find the absolute maximum and minimum values of a continuous function on a closed interval. And there are a set of steps to do that, right? So I'll just show you a reminder of what the steps are somewhere. Where is it? Here we go. So I'll just copy this. So to find the absolute maximum minimum values of a continuous function on a closed interval, we're going to find the critical numbers of the function. Then we're going to evaluate the original function at those critical numbers. Then we will evaluate the original function at the endpoints, compare everything. The biggest number we get out is our max value. The smallest is our min. So here we go. We've got this function. This problem is actually very similar to a homework problem. There's just a slight little difference in it. It's like number 43, except that they had a 4 here instead of 1, and they had x squared instead of x. So let's go through this. First step, I need to find the derivative, right? If I'm going to find the critical numbers, I have to figure out what the derivative of this function is. So when I take the derivative of this function, I have to see that I have a product here between x and then the square root of 1 minus x. So when I run my product rule, I first take the derivative of x, which is 1, then times the square root of 1 minus x. Then add to that, now I need the derivative of the square root of 1 minus x. That's a chain rule. So I first start with the square root. The derivative of the square root of something is 1 over 2 times the square root of whatever was there. Now chain rule, multiply times the derivative of what's inside. So be careful here. The derivative of 1 minus x is -1, right? Because derivative of negative x is -1, derivative of 1 is 0. So I have a -1 there. And then I still have to finish the product rule by multiplying by the first function, which was x. So that's my raw derivative. And now I have to actually do something with this. So I'm going to have to clean this up. So I'm going to just rewrite it first. Okay, I got rid of that 1. Let me bring this -1 and this x. I'm going to put it on top here. And I'm going to make that just a -x on top over 2 square root of 1 minus x. Please do not hesitate to stop me if you have any questions. Okay. That's my derivative cleaned up. Ash, you all right? Yes. Okay. So now what we have to do to find the critical numbers, there's 2 things we have to look at, right? First thing we have to figure out is where's the derivative 0, right? The second thing we have to do is figure out if the derivative doesn't exist anywhere. Okay, we have to pay attention to whether or not that derivative has places where it's undefined. So before I do this, I want us to just take a step back for a second. Let's look at the original function. what is the domain of this? What is the domain of f? So what do we have to be careful with? We have a square root, right? And so we can't have a negative underneath that square root, right? It has to be either, we can have 0 under a root or we can have positives, but we can't have negatives, which means that 1 minus x, right? That's called the radicand. That's the thing under the root, that radicand, 1 minus x, must be greater than or equal to 0 in order for this function to be defined. If it's negative, we're in trouble. So I want to know where is it greater than or equal to 0. I add x to both sides and I get the domain. X has to be less than or equal to 1. So like on a number line, this graph of this function would only exist from 1 to the left, right? That's the only place the graph exists, including 1. I can plug 1 in, that's okay. I just can't plug in anything to the right of 1. Okay, so why is that important? Well, it's gonna be hopefully apparent when we get to this second step over here. So let's first figure out where the derivative is 0. All right, so to do that, I need to set the derivative equal to 0. Yes, I have to solve this equation. And I know it's a little intimidating to look at this and say, hey, how am I going to figure out where this is 0, right? And solve that equation. I know it looks intimidating, but there's kind of a procedure for this. We want to, if we have fractions, which we do, right? Negative x over 2 square root of 1 minus x, and we have another term, right? We have 2 terms. What we'd like to do is combine them together into one term, get them into one fraction first. So I'm going to rewrite the one on the left as over 1, and that means I have to get a common denominator. So I'm going to have to multiply the first fraction on the top and bottom by 2 square root of 1 minus x on the top and on the bottom. That way they will both have the same denominator, right? When I multiply on top, let's look at this first. When I multiply those together, I'm going to have a 2, and then the square root of 1 minus x times the square root of 1 minus x is the same as the square root of 1 minus x squared. So basically the root goes away and you still have a 1 minus x, but because there's a 2 out there, I must put that 1 minus x in parentheses. So that's just multiplying those out. Plus, now the other numerator is negative x, so I'll put plus negative x. And that's all over the new common denominator, which is 2 square root of 1 minus x. Now that, I want to know when that's equal to 0. Any questions? Distribute the 2. So that would give me a 2, then a minus 2x, and then we'll have another minus x. So wouldn't that be a minus 3x on top? All over 2 square root of 1 minus x equals 0. All right, so I've taken something that had 2 terms and I put them together into one. Now I have this fraction equals 0. A long time ago in this class, I told you something that I'm going to remind you of now, and that is anytime you have a fraction, a over b equals 0, anytime you ever see a fraction equal to 0, the only time that can be true is if the top is equal to 0. Let me say that again. A fraction can only be 0 if the numerator is 0. A fraction can only be 0 if the numerator is 0. So right now, I have a fraction equal to 0. So I only have to look at when the numerator is 0. I do not have to look at the denominator. So my next line is just going to be to take the numerator and set it equal to 0. And then this is just a linear equation. I can just move the 3x to the other side and divide by 2. I mean, divide by 3. X equals 2/3. This is my first critical number, Cn, critical number, right? That's a critical number. Something important is happening there at x equals 2/3. Now I need to check, is 2/3 in the interval I'm looking at? Well, I'm trying to find the absolute maximum of this function on the interval -1 to 1. So is 2/3 in there? Yes, right? So I'm going to keep this. I'm not going to throw it away. I'm going to keep it. Questions? Everybody looks so intent today. All right, let's do the second part. The second part for critical numbers is to figure out if the derivative ever does not exist. Okay, is the question. Is there ever a problem with the derivative not existing? So what I'm going to do is I'm actually going to go down to this version of the derivative. I don't like that color. I'm going to go down to this version of the derivative. That was the derivative after I cleaned everything up, right? I'm going to do that over here. All right, and look at that. So I have 2 minus 3x over 2 square root of 1 minus x. And the question is there a number that I cannot plug into this? Is there a number I can't plug into this? And keep in mind the original domain of the function. Remember, the original domain is that x had to be less than or equal to 1. So we're only allowed to look when x is less than or equal to 1. So I'll put that down here. We already know that x must be less than or equal to 1. So from the original domain, right? So can I plug any of these numbers in?
You can plug in a 1.
What happens if you plug 1 in? That's a problem, isn't it?
Mm-hmm.
If you plug in 1, you actually get 0 here, and you get division by 0, don't you? You get division by 0. So it looks like 1 won't work in the derivative. 1 is okay in the original function, right? Can I plug 1 into this? Sure. 1 minus 1 is 0, square root of 0 is 0. That's not undefined. But the derivative is undefined at 1. Because the square root appears in the denominator now, you're going to get a 0 there if you try and plug in 1. So from this, I can say right now, I have a critical number x equals 1, right, is a critical number, because that is where the derivative would not exist. We have 2 critical numbers, yes? Now, it turns out that for this problem, do you all agree that the critical number we have here is actually the right endpoint of the interval? It is, right? It just happens to be. So the next step I'm supposed to do is to plug these critical numbers, right? I'm supposed to plug these critical numbers into the function and then plug in the endpoints into the function and compare everything. So I'm going to do that now. I'm going to take my original function. I'm going to plug in 2/3. I'm going to take the original function, plug in the left endpoint. Take the original function, plug in the right endpoint. See what I'm saying? The right endpoint is also a critical number. I only have to plug it in 1 time, okay? So now I take these and I'm going to get 3 different values out of the original function. The original function over here, I'll just remind you, was f of x equals x times square root of 1 minus x. So let's do this. If I plug in 2/3 for x, I get 2/3 times the square root of 1 minus 2/3, which is 2/3 times the square root of 1/3, which is going to be some decimal I'm going to get in a second. Okay, I'm not going to quite do that yet. And then plug in -1, we'll get -1 square root of, careful here, 1 minus -1. That's going to be -1 times the square root of 2, because you're doing minus minus plus, right? And so that's -√2. And then if I plug in 1, I get 1 square root, and now 1 minus 1. 1 minus 1 is 0. So this is 1 times 0, which is 0. I already can tell you right now, I don't even need a calculator. I can tell you what the max and min is, the absolute max and min. Because look, there's only one number that's negative, right? There's only one number that's negative. So this has to be my minimum value. And then I have 0, and then this number up here is a positive number, right? So it's definitely bigger than 0. So this has got to be my maximum value. So the goal of the problem was to find where do you, what is the maximum value? What is the minimum value? So the maximum value is whatever this number is. The minimum value is this, -√2. And also keep in mind, where do they occur? When I plug in 2/3, that's where I should have a max. And when I plug in -1, that's where I should have a min, my minimum. So let's take a look at the graph of this. I have it ready to go. This is the graph of that function. Okay, that's the graph of that function restricted to -1, 1. In fact, let me do it this way. X square root of 1 minus x. Okay, that's the whole function. That's everything. Okay, that's the entire function. I'll make it dotted. That's the entire function. If I take that function and just restrict it between -1 and 1, I get just that piece. Okay, between -1 and 1, right? You can see that. And so what we found is that when you plug in -1, you get a minimum value of -square root of 2 right there. And then the other one happens at 2/3. Let me see if I can do this 1/3. Yeah, okay, that'll work. So you can see this is 1/3, this is 2/3. So you can see I have a maximum value right there. All right, does everyone understand what we've done? We took a picture or a graph, we cut it off, looked at an interval, we found the highest and lowest points on that graph. Okay, I can proceed. Find the absolute maximum minimum value of the function f of x equals 3x minus 4 over x squared plus 1 on the interval -2 to 2. All right, got to start with the derivative, right? So I take, you know what, let's start with the domain. Let's look at the domain of this. What's domain of f, dom f? Are there any numbers you cannot plug in? Be careful. You can never make that denominator 0, ever. You can't. You can try, but you're not going to. Because when you take a number and square it, right? Hold on. So annoying. Okay, so when you take a number and square it, it's got to be positive, unless you plug in 0, right? If you plug in 0, 0 squared is 0. So the worst case scenario you're going to have here is a 0 plus 1. That's always going to be positive, right? So you're never going to get 0 down here. So you'll never have division by 0. So the domain of this should be everything, -infinity to infinity. So if we look at the graph of that, it should go in both directions forever. We should have no places where we have any issues. That means if we get any critical numbers, we're going to include them because our original domain, or sorry, I take that back. If we get any critical numbers, we're going to need to look at them, make sure they live in this interval, but we don't have any domain restrictions at all, right? In terms of the function. The only restriction we have is that we can only be looking between -2 and 2. Okay, derivative. Quotient rule, right? Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So, you know, this is a good point for you to do a little reflecting, self-reflection. How easy is that quotient rule for you? Are you still taking 10 minutes to do that? Or are you doing that almost mentally, just kind of like I did? You want to be getting to that point, and hopefully you're to that point where that quotient rule is really nothing, right? Now, setting it equal to 0 and solving all that, yeah, that's going to be more of an issue. But the quotient rule itself should not be the thing that's hanging you up. All right, I need to figure out where this derivative is 0 and where it could be undefined. So let me clean it up first. Distribute the 3 through the top. Distribute the -2x through. Double check me on that. Is that right? Did I do that right?
Plus 8x.
Yeah, 8. Thank you. Better? Okay, let me get my x squared terms first, -3x squared, and then I have plus 8x plus 3. all over my x squared plus 1 squared. There's my nice cleaned up derivative, right? Nice and cleaned up. Let me figure out where that derivative is 0. So I'm going to take that derivative, and because my derivative is a single fraction, right? It's a single fraction. I only have to look at where the numerator is 0. So this really just means I have to look at negative 3x squared plus 8x plus 3 and set it equal to 0. That is a quadratic equation, and I'm free to use any technique I have for that, including the quadratic formula if I need it to. I think it factors though. Let me see if I can get this to factor. I hope it factors. I'm going to go with, does it factor? Shit, maybe not. No. I would need a negative, maybe. Hold on. Negative 3, and no, that's not going to work, is it? That doesn't work. Negative 3x squared, positive 9x. Oh yeah, minus x. So that does work. Okay. Got lucky. Okay, so you have the quadratic formula if you're having trouble with that part, right? You have the quadratic formula. You get these answers. Yes. So I'm going to set each of these factors equal to 0. And I get some solutions here. Negative 3x equals 1. Move the negative 1 to the other side. Divide by negative 3. So negative 1/3 and then positive 3. Those are my two potential critical numbers. What do I need to check though?
Whether they're on the domain.
Yeah, are they in the interval we're looking at? So we're only looking between -2 and 2, right? And look, one of these is 3. That's outside the interval I'm looking. That means I'm throwing that one away. Negative 1/3 is in there. So I'm going to keep it. We good? Step 2. Does my derivative ever not exist? Well, let's take a look at that derivative over here. Well, it's a fraction, right? So the only issue I would ever have is potentially if the denominator was ever 0. But we already looked at this, right? X squared plus 1 can never be 0. So I have no issues, right? There's nothing that's going to cause that to ever be undefined. So, nope. Okay. Nope. Nothing here. Nothing to worry about with that, right? No critical numbers in terms of the derivative not existing. And so now just plug the critical numbers and your endpoints into your original function. The biggest one you get is your max, the smallest you get is your min. So here we go. Into my original function goes negative 1/3. Into my original function goes the left endpoint, -2. Into my original function goes the right endpoint, 2. My original function, in case we've forgotten, which I have, what was it, 3x minus 4 over x squared plus 1? Right, that was it. Yeah. All right, let's plug in negative 1/3. So if I plug in negative 1/3 right here for x, 3 times negative 1/3 is negative 1. And then minus 4. So I get minus 5 on top. And then I have negative 1/3 squared, which would be a positive 1/9 plus 1. So I get negative 5 over, put these together. This will be 10/9, get a common denominator, put those together. And then multiply by the reciprocal. And so you get negative 45 over 10, which is negative, what, 5 goes in there, 9 halves, is that right? Negative 9 halves, seems right. 5 goes into 45 9 times. 5 goes into 10 twice. Yeah, 9/2. I could have just reduced it here, 1 and 2, whatever, all works the same. Okay, that's what happens when I plug in -1/3. When I plug in 2, let's see, I get 6 minus 4, it's 2 on top. And then when I plug in -2 on the bottom, when I square -2, it's +4, plus 1 is 5. So I get 2/5 there. When I plug in +2, wait a minute, hold on. I just screwed that up, didn't I? Sorry, I was plugging in, I meant to plug in -2, I plugged in +2. -2 into this gives me -6 minus 4. That's -10 over 5, which is going to give me -2. And then when I plug in the +2, I get 6 minus 4, which is 2 over 5. And remember, this is a -4.5. All right, so my maximum value is the biggest number I see here. So this is my max. And then the smallest number I see is -4.5. So this is my minimum. So when I go graph this, at -1/3, I should see the minimum. And at 2, the right endpoint, I should see the maximum. Let's take a look. There's the graph. Okay, there's your graph right there between -2 and 2. There's the picture. And you can see that down here at -1/3, we have the minimum value is -4.5. And you can see the max is going to be that right endpoint right there. At 2, it was 0.4. Right. Was that our max? Yeah, 2/5, which is 0.4. Questions? Last one. I thought I'd do a trig, something with trig, because that always gets people. So find the absolute maximum of this function on this interval. So we've got f of theta. I switched up the variable. I used theta instead of x. Okay, big deal. We're going to just take derivative, right? So derivative of this, f prime of theta is going to be, well, derivative of theta is 1. Derivative of cotangent theta. Okay, so maybe you don't know that off the top of your head, but you know it's in your formula sheets, right? And also this is going to be chain rule, because look what's inside. 1/2 theta. We'll have to take derivative of that in chain rule, but first we have to take the derivative of cotangent. The derivative of cotangent of something is
1 over tangent, so 1 over secant squared.
no. Look it up.
Secant tangent.
No, look it up. Formulas, let's go to our derivatives. Where's the derivative of cotangent? Oh, there's cotangent, right? Formula 18, the derivative of cotangent of x is negative cosecant squared of x. Negative cosecant squared of x. That's what we need. So this should be negative cosecant squared of x, but for us it's not x, it's 1/2 theta, right? So now I've taken the derivative of the cotangent part. Chain rule, got to go inside and take derivative of 1/2 theta. What's the derivative of 1/2 theta?
1/2.
1/2. All right, there we go. We're done with the derivative. Let's clean it up. 1 minus 1/2 of cosecant squared of 1/2 theta. All I did there was just, change that plus minus there to a minus, and I brought the 1/2 out here in front. Remember, you cannot touch this 1/2 theta, right? You can't, it's trapped inside that cosecant squared. So There it is. That's my cleaned up derivative. There's not much more I can do to that. Any questions? Let's figure out where it's 0. Where's my derivative 0? Well, 1 minus 1/2 cosecant squared of 1/2 theta equals 0, setting it equal to 0. Ooh, geez. All right. So we're back in pre-cal now. So here's what I'm gonna do. I'm gonna move everything that was negative to the other side of the right side of the equation to make it positive. So basically all that cosecant squared stuff that was minus 1/2 cosecant squared, 1/2 theta, I moved it to the right. I'm gonna multiply both sides by 2. That'll clear out that fraction. All right. And now we have to figure out what this is. Okay, I don't like that squared. I'm going to take the square root on both sides. Okay, I'm going to take the square root on both sides. So I'm going to take the square root on the left and the square root on the right. When I do the square root on the right, the squared on the cosecant goes away. Is that fair? Square root both sides. But because I did the square root on both sides, I have to do what on that square root? Plus or minus, you've got it. We initiated the square root, right? So when we initiate the square root, we have to do plus or minus. All right, that might look terrible. Okay, that might look terrible, but there is a relationship we have. And that is, back from pre-cal, cosecant x is the same as the reciprocal of sine, right? That's what cosecant means. So if I wanted to, I could switch this into a sine by doing this. I can make this sine of 1/2 theta equals, and then what I do is the reciprocal of this one. So basically, like, this is over 1 and this is over 1. So like when I reciprocal both sides, this becomes 1 over plus or minus the square root of 2. So the cosecant flips over and becomes a sine. And then the root positive or negative root 2 flips over and becomes a 1 over positive or negative root 2. Is that okay with you or not? Some people aren't going to be okay with that, so I'm just going to go fast over here. This is what I did. I rewrote the right side like this. Okay, I rewrote cosecant of 1/2 theta as 1 over sine of 1/2 theta. And then I multiply both sides by sine of 1/2 theta, sine of 1/2 theta. It cancels over here. And then I divided both sides by plus or minus root 2. Divide this side by plus or minus root 2. And you wind up getting sine of 1/2 theta equals 1 over plus or minus root 2. That's the algebra. But if you, the easier thing is just to say, hey, to turn cosecant into sine, flip it, but then you have to flip the other side as well. Okay. Y'all okay? So I want to know when sine of 1/2 theta is equal to this. Now, this is tricky because you have to recognize this from pre-cal. So let's take a little detour. If I had 1 over the square root of 2, we could rationalize the denominator. We can multiply the top and bottom by root 2. And when we do that, we get root 2 over root 2 times root 2 is 2. In other words, this left-hand side could be plus or minus root 2 over 2 instead. And the reason why that's important is because you should all recognize that square root of 2 over 2 is at some of the common angles on the unit circle. So now this, I'm thinking pre-cal again. I'm saying where on my unit circle is the y coordinate? Why am I thinking y coordinate, not x coordinate?
Because that's what sine is.
Because sine is y coordinate. So where on the unit circle is the y coordinate plus or minus root 2 over 2? Well, the y coordinate here at 45 degrees, right? The y coordinate is root 2 over 2. Over here, it's also root 2 over 2. Down here, it's negative root 2 over 2. And over here, it's also negative root 2 over 2, right? My y coordinates. So isn't that at multiples of this original angle here, that original angle, that's pi over 4, isn't it? That's pi over 4. And then to jump to another one, I just need to add another pi over 4. And then jump to another pi over 4, pi over 4, pi over 4, pi over 4. So to, sorry, no, I did that wrong. I did that completely wrong. Ignore me. I just had a brain fart. Okay, my original angle was pi over 4, right? To jump to another one, I need to add pi over 2 to get to another one. And then to get to the next one, another pi over 2. And then to get to the next one, add another pi over 2, right? And then to get back to where we were, add another pi over 2. So the general solution to this is start at pi over 4 and add to it n multiples of pi over 2. Look, I do realize that this is a point in the class where you're like, holy shit, pre-cal actually was supposed to like know that for this, right? Like, I get that. I'm not expecting everyone's like at this level where they completely understand this, but this means you need to go and like maybe get freshened up on this, all right? Hopefully you're seeing what I'm doing. You're like, okay, that rings some sort of bell from the past. This is my general solution. So what we want is that the argument in the sine function, 1/2 theta, must be equal to this. Now multiply both sides by 2. And when you multiply this side by 2 and distribute through and then multiply here, it'll go away. You'll get pi over 2 plus n pi. Right now, I have an infinite number of critical numbers. There's an infinite number of these, aren't there? However, I'm only supposed to look between where? Pi over 4 and 7 pi over 4. Pi over 4 and 7 pi over 4. So let's go back to our unit circle. The angles that we can talk about have to be between here, that's pi over 4, and then 7 pi over 4 is down here. So that's pi over 4, that's 7 pi over 4. So we can have any angles over here in this, anywhere in those regions. So let's start looking at some different values of n. If n is 0, what's theta? What's theta if n is 0?
Pi over 2.
Okay, is pi over 2 in this region?
Yeah.
Yeah, it's straight up, isn't it? Straight up. Okay, so that works. That is a critical number. Okay, let's let n be 1. If n is 1, we get pi over 2 plus pi. This is pi over 2 plus 2 pi over 2. I'm getting a common denominator, put those together. When you add those, you get 3 pi over 2. Is 3 pi over 2 in here? Yeah, where is it?
Down there.
Straight down, right? Straight down. So this first answer was the angle that goes straight up, right? That's pi over 2. And then this second answer we got, 3 pi over 2, is actually the angle that goes straight down. But there aren't any more, right? If I do n equals 2, I'm going to go past 7 pi over 4. So those are my only two critical numbers. This problem's tricky, huh? Theta equals pi over 2. Students hate trig problems when it comes to this stuff. Theta equals pi over 2, theta equals 3 pi over 2 are my only two critical numbers. All right, I'm not done. I was just step 1 there. I was just figuring out where the derivative was 0. I now need to go see if the derivative is ever undefined. Wow, okay, so let's go, where's my derivative? Here's my derivative, right? That's my cleaned up derivative. Let me do step 2. I'm doing a different page. Are y'all feeling ill? Are y'all okay? Is the derivative ever not exist? Question. So here's my derivative. Well, this, we actually could have an issue here because think about what this really means. 1 minus 1/2. This is really, I could look at it as 1 over sine of 1/2 theta squared, right? Cosecant we said was 1 over sine. So if I replace cosecant with 1 over sine and then square it, there is a possibility here that I would get division by 0, isn't there? I need to ask myself this question. When is sine of 1/2 theta equal to 0? So now you're going to play the same exact game we just played, except we're now looking on the unit circle for where the y coordinate is what? 0, right? 0, which happens here and here. So at 0, and then we would have to add pi to get to this, and then pi to get back. And we could keep on adding multiples of pi. So now what we would need to look at is when 1/2 theta is equal to 0 plus pi n. Which means 1/2 theta equals just pi n, which means theta is just 2 pi n. Any multiple of 2 pi. But, where were we restricted again? Between pi over 4 and 7 pi over 4, right? That's where we're restricted. So we're only allowed to look between pi over 4 and 7 pi over 4. That's all, only places we can look at, right? And our thetas are any multiples of 2 pi. So if I let n be 0, I get theta is 0. Would that work or no? Is theta equals 0 in here? No, right? Theta equals 0 is over here. If I let n be 1, theta is, let's see, 2 pi times 1 is just 2 pi. And now you've gone too far. You've gone all the way around back to here. You're outside of that interval. Which means, nope. No critical numbers from this. All right. How many critical numbers do we have? I forgot. These two, right? And the endpoints are going to get plugged into the original function. So I need the original function evaluated in 4 different places. The 2 critical numbers, the 2 endpoints. The endpoints I remember, pi over 4, 7 pi over 4, and then pi over 2, 3 pi over 2. Pi over 2, 3 pi over 2. And those are getting plugged into the original function, which is this. You'll need a calculator. So if I plug in pi over 2, I get pi over 2 plus cotangent, oh, not cosine, cotangent of, okay, what happens if you plug pi over 2 right here? You multiply times a half and get pi over 4, right? So cotangent of pi over 4. Okay, that's pi over 2 plus, okay, cotangent is the same as tangent sine over cosine, right? So cotangent is cosine over sine. So this is the same as cosine of pi over 4 over sine of pi over 4. Hey, but wait a minute, at pi over 4, that's right here, this pi over 4, aren't the x and y coordinates exactly the same? So shouldn't this just be a 1, right? Should this be 1? They're the same values, so you're going to do whatever the x value is here and whatever the y, divide them, you get 1. So this is just pi over 2 plus 1. Okay, whatever that is, I'll figure that out in a minute. Let's plug in 3 pi over 2. So we plug in 3 pi over 2, we get 3 pi over 2 plus cotangent of 3 pi over 4. Where did I get 3 pi over 4 from? Multiplying half, right? Half of 3 pi over 2 is going to give you 3 pi over 4. Where the heck is 3 pi over 4? Isn't that here? Isn't that red one, 3 pi over 4? Are the x and y coordinates there exactly the same? Aren't they off by a sign? Isn't one of them negative, the other one's positive? Right? So when you do the ratio, you don't get 1, you actually get what? -1, right? -1. Y'all aren't talking to me today. I'm sad. 3 pi over 2, and that's going to be -1. Let's try pi over 4. So we get pi over 4 plus cotangent, and this is going to suck, pi over 8. Why does that suck? Because pi over 8 is not a common angle. So I'm going to have to use my calculator for that. And then on the one below it, 7 pi over 4 plus cotangent of 7 pi over 8. So if I were using my calculator, I mean, you don't really have a cotangent key, so you would have to do like pi over 4 plus cosine of pi over 8 over sine of pi over 8. And then on this one down here, you'd have 7 pi over 4 plus cosine of 7 pi over 8 over sine of 7 pi over 8. And you would need to make sure that you're in radian mode on your calculator when you were doing that. I'm going to cheat. I'm going to just go to the graph. We got to figure out which of these is the biggest and smallest. All right. So I'm going to go to the graph. Here's the graph of the function. Restricted between pi over 4 and 3 pi over 4. Okay, there's the restriction. When you plug in pi over 4 into this graph, why is it not letting me? Okay, when you plug in pi over 4, you should get about 3.198. When you plug in pi over 2 as a decimal, you get 2. Wait, did I say negative? When you plug in, something is wrong here. Hold on. When you plug in pi over 4, you should get 3.181, something like that, something close to that. When you plug pi over 4 in. When you plug in pi over 2, you get about 2.5. When you plug in 3 pi over 2, you should get 3.712. And when you plug in pi over 4, 7 pi over 4, you should get about 3.088. So this is your max, and this is your min. There they are. The maximum value is 3.712. The minimum value is 2.571. That problem probably made your head spin a little bit there, huh? All that pre-cal stuff in there. Was the derivative bad? What if you messed the derivative up, right? If you mess the derivative up, it's over, right? It's pretty much over at that point. So we want to be careful.
I have a question.
Mhm.
So
Hey.
when you change that cosecant to the sine in the derivative,
Oh, in the derivative. Right here.
yeah. So you said cosecant is 1 over sine, right?
Mm-hmm.
So why did you just put that as sine? Wouldn't it be 1 over sine?
It is. So if I did do it, this is what would happen. If I left the left side alone, it would have been plus or minus √2 equals, then the right side would be 1 over sine of 1/2 theta. That's what it would be, right?
Right.
But now I have to get the sine of 1/2 theta out of the denominator. So I'd multiply both sides by sine of 1/2 theta.
Oh, okay, okay. Just to solve for the
To get
theta.
to get this thing off the denominator, I'd have to multiply it on both sides.
Okay.
And then the plus or minus √2, I would have to divide on both sides to get it out of there so that the sign on the other. So that's what I did here, right?
Yeah. Yeah, that makes sense.
I multiplied both sides by the sine of 1/2 theta, it went away, and then I divided both sides by plus or minus √2, and it appears on the bottom on the right-hand side.
Yeah.
Which is really just the same thing as taking, here's another way I can explain it. If I wrote cosecant of x equals y, if I wrote that down, then you can, the next line you could write is sine of x equals 1 over y.
Yeah.
That's basically what I did.
Okay.
But technically, algebraically, I'm clearing the fraction out, and you know, the non-technical is just you're just flipping both fractions over.
That makes sense. Thank you.
Mhm. All right. 4.1. We're done. Would you all agree that the actual concept is not that crazy in terms of what we do? Like if you have a function on a closed interval, you take the derivative, right? You figure out where it's 0, you figure out where it doesn't exist. You plug those points in, you plug the endpoints in, you compare, you're done, right? Like, so systematically, like the approach isn't that bad. It's the actual execution of it. It's making sure you get the derivative correct, making sure you set it equal to 0 correctly. And in terms of, you know, what you're going to solve, it's going to, the problems are going to vary, right? Like the first problem we did, what did we have to solve? When we set the derivative equal to 0, we wound up solving a linear equation, no big deal, right? Second problem, okay, well, we had to solve a quadratic equal to 0, no big deal. I mean, not no big deal, but not that bad. But then we get this one, and it's like, holy crap, we got to set the derivative equal to 0. That's a trig equation that had a set of general solutions based on the unit circle, and then we have to figure out which of those general solutions fall within the window we're looking, right? So, I mean, it's a much more complicated problem, right? Okay, we're done. We're moving to 4.2, mean value theorem. Y'all want to take a little 1 minute? Let's take a 1 minute break. I'm going to refill my drink here. I think it needs to be a little bit stronger for the rest of the class. I meant stronger coffee, just in case there was any confusion there. All right, mean value theorem. So to start this off, I'm gonna get into the notes, but I just want to remind you of something. We are taking a little detour here for a moment for this section. All right, we are going to get back to finding the highest and lowest points on the graph. This section, it's almost like we're just taking a pit stop for a minute. All right. So just as a reminder, if I give you a function, let's say, for example, this is time and this is distance. And I've used this example before, like let's say you're going to drive to Austin or something. So you drive and you wind up getting to Austin. So maybe it takes you 2 hours, right? 2 hours. Time will be measured in hours. And maybe you went, I don't know how far Austin is, but let's just go with 90 miles. All right. That's how far you went. So, you were speeding up, slowing down, traffic, whatever. If you look at the line that connects the two endpoints together, the straight line, right? That's called a secant line, secant line. And if we find the slope of that secant line, that would be the rise over run. Well, the rise was 90, right, miles. And the run was the distance on the bottom, which was 2 hours. And of course, 90 divided by 2 is 45. So it would be 45 miles per hour. That would be your average speed. Your average speed. So in other words, if you give me any function, okay, any function, and you start at one point and you end at the other, and you connect these two together and you find the slope of that, that will be your average rate of change. Your average rate of change, whether it be miles per hour, doesn't matter what you're measuring. The slope of the secant line is your average rate of change. Now, in math, when we talk about the word average, okay, there's another name for the word average. And you may have heard it if you've taken any statistics classes. Instead of the word average, we can use the word mean. The mean is the same as the average, all right? So if I say, oh, you've got 5 test scores, take the average. Well, I could tell you to find the mean, and it's the same thing, all right? So when we talk about the average speed, we could say the mean speed, or we could say the mean rate of change. So mean as an average, not mean as not a very nice person, right? That's the other definition of mean. Here, mean means average. Okay, the mean value theorem. Let's get to it. All right, we're going to start with a theorem, and it's not the mean value theorem. By the way, I'm going to abbreviate the mean value theorem, MVT, but we're not talking about the mean value theorem yet. We're going to first talk about Rolle's theorem. Okay, so here's what Rolle's theorem says. Let f be a function such that, first, f is continuous on some closed interval. So continuity we've talked about is that you can draw it without picking up your pencil. So you have a graph that you can draw without picking up your pencil, and it goes between 2 points. Hold on, let me reevaluate this thing, evaluate the notebook. Give it a second. Okay, so we have a function that you can, it starts at some point A, ends at some point B, and we can draw a curve between the 2 points without picking up our pencil. All right, so let's say we start with that. Then I tell you that the function is differentiable, which means that everywhere inside that interval, you can actually take the derivative, meaning we don't have any jumps or breaks. Well, we kind of knew that because it was continuous, but more importantly, we don't have any corners or cusps or vertical tangents, right? So no cusp, corners, or vertical tangents. Also, the third condition is that the 2 endpoints have to have the same value. So the 2 ends have to be at the same height. Okay, so it's this picture right here. What Rolle's theorem says is that if we have this scenario, that there must exist some number C within the interval AB, meaning there must be, here's A, here's B, there has to be somewhere in here some C such that the derivative at that value is 0. So look at this visually. Do you all agree that if we connected these two endpoints together with a secant line, the slope of that secant line is 0? Yes? Rolle's theorem says, well, then there's got to be somewhere on your graph where the tangent line must also be 0. Do y'all see where it is? Right about there. Has to be. Rolle's theorem says it's guaranteed. Guaranteed. Let me give you a different example. So here's where it happens. You connect these two endpoints together. The slope of that secant line is 0. And somewhere in between A and B, we're going to get a tangent line that's also got a slope of 0. Let's look at a different curve. Look at that curve right there. Notice the two endpoints are the same, right? Same height, continuous function between them. Rolle's theorem says there has to exist at least one point where the tangent line will also be 0. Well, here in this example, it happens in 2 places. Rolle's theorem guarantees us at least one. There must exist at least one place where this is true. Do y'all see it visually? Do y'all understand the theorem visually that this should do this? Let's look at a third example. A straight line. Well, then every point in here, right? It doesn't matter where the point is. Every point in here, the slope of the tangent line would be equal to 0. So you could have just one point where it happens, 2 points, 3 points, 4 points, or it could happen everywhere. Rolle's theorem just guarantees us the existence of at least one. Okay? Now, the mean value theorem, not this theorem, the mean value theorem. I'm actually going to start with the picture. Okay? This right here is Rolle's theorem, right? The two endpoints are in the same place. So Rolle's theorem guarantees there's a place where the tangent line is also flat. What the mean value theorem says is this: even if you were to change the heights of the two endpoints where they're not the same anymore, now you should have somewhere between A and B, not where the derivative is 0, but where the derivative is parallel to the line connecting these two endpoints. Do y'all see? It's just Rolle's theorem tilted. Rolle's theorem tilted. Yeah? So here's the actual theorem. Let f be a function such that first it's continuous. Okay, so we have the same condition, has to be continuous, must be differentiable, so we don't have any corners or cusps. Then there exists a number C such that the derivative is equal to this. Now, I want to go back to Rolle's theorem for a second. Rolle's theorem said that there's got to be a number C where the derivative is 0, right? Where the derivative is 0. Well, Rolle's theorem said the derivative must be 0 because, remember, the two endpoints were at the same place. So that secant line, right? This secant line has a slope of 0. So Rolle's theorem says, yeah, well, there's got to be a place then where the derivative is 0. The mean value theorem says, well, no, we won't have that same condition because the two endpoints aren't the same. I'm not saying that the derivative will be 0. I'm saying the derivative will be parallel to the slope of this line, right? So let me take this. Oh, let me take this. Let me take this here. So the mean value theorem says there's got to be some value C in here that when I look at the derivative at that value C, right, the slope of that purple solid line, that must be equal to the slope of this, right? Equal to the slope of that. But what's the slope of that? We could draw a triangle. The rise and the run, right? Well, the rise, isn't that just the difference of the y coordinates? Well, this y coordinate is f of b minus this y coordinate, which is f of a, over the run, which is just the difference of the x coordinates, b minus a. That's the mean value theorem. So that's it. That's the theorem. So let me show you how we would use this, like what sort of problem you would be asked to do. All right, because these problems are a little strange. Verify the mean value theorem for f of x. We'll start simple. 3x squared minus 6x on the interval 0 to 3. I'll give you a minute to write that down. I actually don't have this ready to go, so I'll get this ready while you're writing that down. So let me graph this. 3x squared, squared minus 6x. And we're only looking between 0 less than x. 3. Okay, so there's the graph of that function between 0 and 3. What we're trying to do is this. We are saying that if we connect these two endpoints together, that has some slope, right? That's a secant line. Somewhere in here, somewhere between 0 and 3, somewhere between 0 and 3, somewhere on this number line, I should be able to go to that point. I think it's about right here. Maybe about right there, that there's some value c that we need to figure out, that if we go down to the function and look at the slope of the tangent line there, it will be parallel to that blue one. And we need to figure out what that value of c is. All right. That's the goal. So let's do it. All right, so first thing I'm going to do is I'm going to find the derivative of this function. So the derivative of this function is easy, right? Easy. I hate to say things are easy unless they're really easy. Do y'all agree that's easy? That's a derivative of that function. Now, what do we want? We want to show there is a c in the interval 0, 3 such that when we take the derivative of the function evaluated at c, it's equal to the slope of the secant line, which is f of b minus f of a over b minus a. Here, a and b are the two endpoints, a and b, right? So we really want to show that there's some value c that when we take the derivative there, we get something that is equal to f of 3 minus f of 0 over 3 minus 0. Okay, let's keep going. That means we've got to figure out somewhere where the derivative is equal to, well, what's f of 3? That's just 3 being plugged into the original function, right? So what happens if you plug 3 in here? Let's see. 3 squared is 9. 9 times 3 is 27. take away 6 times 3 is 18. So 27, take away 18 is 9, right? You get 9. So we had 9 there. Minus, what's f of 0? So plug 0 in here. If you plug 0 in here, you get 0. And then on the bottom, 3 minus 0 is just 3. And that's just 9 over 3. So don't we want to show that there's some value where the derivative is equal to 3? Right? Okay, but what was the derivative? This was the derivative, right? Up here, that's what the derivative is. So what I'm going to do is I'm going to say, I'm going to take that derivative up there, 6, but I'm going to replace the x with c. 6c minus 6 must equal 3. And now solve for c. Add 6 to both sides. Divide both sides by 6. 3/2. At 3/2. That's where I should have a tangent line that is parallel to the secant line. So the question was asking, verify the mean value theorem. The mean value theorem says there must be a point somewhere between 0 and 3. There's got to be one, where when we look at the slope of the tangent line, at that point, it should be parallel or equal to the slope of the secant line. So this is the slope of the tangent, and this is the slope of the secant, connecting the two endpoints. And we're saying there's somewhere where they're equal, right? Parallel. Basically saying they're parallel lines. Let's verify with the picture. We said it was the point 3/2, right? Let me see here. 3/2. Let me change something here. Make this a little easier for myself. Okay, that's j of x. So I want us to plot the point 3/2, j of 3/2. Okay, there's the point on the graph that we found, right? When we plug in 3/2, 1.5, it spits out this point. We have the line connecting the two endpoints together, here to here, right? And if I take the tangent line there, it should be parallel. Let me see. Let me think for a moment. Okay, y minus j of m equals j prime of m times x minus m slider m. Okay, so here I have it doing my tangent line for me. Let's let m go from 0 to 3. All right, so there we go. I have this thing doing tangent lines for me. All right. Do you all agree that when I get to 1.5 right there, that tangent line right there looks parallel to the reddish pinkish one? Yeah. We have found the point, the x value, the c value, where your tangent line is parallel to the secant line. Every continuous function on a closed interval has that happen. And it could be at more than one point, okay? But you're guaranteed at least one. Let's do another one, yeah? How about this one? How are we doing on time? We're okay? I want to do a harder one. How about verify mean value theorem for f of x equals x over x plus 1 on the interval 1, 4. I'll put that back up. I'm going to graph it first, all right? So let's call this k of x equals x over x plus 1. And we're only going to look between 1 and 4. All right, so here's our graph. It's kind of hard to see. I'm going to exaggerate it quite a bit. There we go. That kind of exaggerates the graph so we can see what's going on. So if we connect these two endpoints together, right? If we connect these two endpoints together with a straight line, there's some place in the function where we're going to have a tangent line that's parallel, right? We got to find where it is. All right, so first things first, let's find the derivative. The derivative of this is going to be 1 times x plus 1 minus 1 times x all over 1 plus x, that quantity squared. Quotient rule, right? Which is just, I think, 1 over 1 plus x, that quantity squared. Because the x's on top would cancel, right? When you distribute 1 through here, you get x plus 1 minus x. So that's my derivative. All right. So now what do we want to do? We want to show there exists a C in the interval 1, 4 Hey, hold on a second. There's some sort of alarm going off. So I'll be right back. You can work on this for a minute. I'll be right back. Okay, it was not in my house. So we want to show there exists a C in the interval 1, 4 such that what the derivative at that point C is equal to the slope of the secant line, which for us would be f of b minus f of a over b minus a. So that right there is like the master formula that you have to work with for every mean value theorem problem. You got to work with that. So that means I need f prime of c, the derivative at c, to be equal to, for us, a is 1 and b is 4. So this will be f of 4 minus f of 1 over 4 minus 1. The thing that's going to suck about this is we're going to have some fractions here. I want the derivative to be equal to, all right, f of 4. So we have to plug 4 into the original function, and we get 4 over 5. Minus, now we plug 1 into the function, and we should get 1 over 2. And that should all be over 4 minus 1, which is 3. Y'all following?
How did you get 4 over 5?
Okay, so I'm plugging 4 right into the original function. So plug in 4 here.
Oh, sorry, I was looking at the wrong. I was looking at the derivative function.
Okay, yeah. So I say it subtly, but I say it intentionally. We're plugging 4 into the original function, right? This is going to become even more confusing next class, because next class we're going to be plugging things into the derivative, and you're going to start forgetting what gets plugged into what. So this 4 is getting plugged into the original function. The 1 is getting plugged into the original function, right? That okay? Right. Unfortunately, I have to combine those fractions together with a common denominator. So, I mean, got to put those together. So that should be 3/10, I believe, on top. And then all over 3. And then that's same as 3/10 over 3/1. So you can multiply by the reciprocal. So you should have the derivative at some value C must be equal to 1/10. Now, what is the derivative? Well, here's the derivative, right? So if I plug C into this, I will get 1 over 1 plus C, that quantity squared must equal 1/10. Now let's do like a cross multiply. 10 here, this here. You'll get 10 equals 1 plus C, that quantity squared. Let's take the square root on both sides to kill off the squared on the right. Because I'm doing that, I do plus or minus. And then let's subtract 1 on both sides. So plus or minus the square root of 10. Let's subtract 1 from that. And that's what C is. So I got 2 answers here, don't I? Got 2 answers. Okay, get on your calculator. What's the square root of 10 approximately equal to? It's about 3.16, somewhere around there. So this is plus or minus 3.16 minus 1 equals C. So let's look at those 2 different answers because there's 2 different ones, right? I could do 3.16 minus 1, and I could do 3.16 plus, sorry, I did that wrong. Minus 3.16 minus 1. So I'm looking at the 2 different scenarios. This one is 2.16. And this one is negative 4.16. Now, are both of these answers in my interval? No, right? Only one of them. The only one that's in there is 2.16. This one's outside. Questions on the work here? Shall we check it visually? I'm going to go ahead and do this like I did a minute ago. Y minus K of M equals K prime of M times X minus M. There's my tangent line. Okay, there's my tangent line. And let me get the secant line in here. Okay, so my secant line, I'm not going to have the computer draw it. It's going to be a little bit too much work. So if I connect these 2 together with a straight line like this, okay, now let me go to the point that it's supposed to happen. Oops, oh, that's terrible. The point that it's supposed to happen was, what was it, 2.61 or 16?
16.
2.16 comma K of 2.16. So right there at that point is where it should be parallel. Let me drag it over there. Right about there. They look pretty parallel to me. Okay, that's the idea, right? There's really nothing else. What I would like for you to do for homework for this, we're not done. I have one more thing I want to show you, but as far as the homework, we can be done with this. So here's what I want you to do. I don't want you to do this assignment. Okay, I just want you to do 9, 10, 11, and 12. So 9 through 12. All right, I'm debating. There's 2 things I want to show you, but I can only show you one. So I'm debating right now which one I want to show you. One of them probably is, well, I'm going to go with what I like. Okay, let's do that. So I have a question for you. All right. I don't know if I'm going to be able to finish this in time, but I'll try. Let's say we have a race. We're going to look from the top. This is the starting line. Okay, and then this is the finish, right? And we have two cars that are going to race. We have car A and we have car B. They're going to start at the starting line, try and race to the finish line, all right? So here's what I'm going to tell you about what happens during this race. They race each other, okay? And when they get to the finish line, they tie. Okay, they tie. I'm telling you, this is a theoretical problem. So let's imagine that they started exactly the same time and they got to the end of the race and they tied. Throughout the middle of the race, I'm not going to give you any other information. Okay, it's not necessary. Just that they started together and they tied at the end. Right, so here's my question for you. Is there a point in time during the race where both cars were going the same speed? Think about, don't answer yet. Think about the question. Is there a point in time during the race where both cars were going the same speed? Not at the start or end. During the race. Okay. So of course, when they both start, they're not moving, right? So it's like, go, and then they take off, right? And then when they get to the finish line, right, they're at the same place at the finish line. So forget the beginning of the race and the end of the race, just somewhere in between. Is there a point in time where both cars were going the same speed? Think about it. I'm going to give you 30 seconds to think about it. We're going to do a poll. So the answer is either yes or no, right? The answer is yes or no. You'll let me know in the poll what you think. Anybody have a question about my question? Anybody need me to clarify anything? Jeopardy music playing in the background. Fifteen more seconds. Y'all are going to have some explaining to do here. %90 of you almost think that there is some point in time where both cars are going the same speed. All right, and then 11% say, nope, there's not. So let me start with the overwhelming majority of you who said yes. Justify it. Explain to me why.
I'm just shooting my shot, but I guess I figure that, you know, there has to be, if they finished at the same time, there has to be a point at which, you know, one of them was slowing down while the other one must have been increasing in speed, just so that they could eventually catch up to each other, I guess you could say.
Yeah. That seems like a reasonable explanation. If they start together, right? They start together and they tie, then it seems like somewhere in the race they would have to be like side by side maybe again. And maybe when they're side by side again, that's when they're going the same speed. Maybe.
I was thinking it like they're on the same track, but one takes kind of like a curve. And so like kind of how we were looking at a graph with like a tangent line on it. That's
Mhm.
like where they meet up.
Okay. Yeah. I mean, this is good. These are good explanations. How about somebody who says no? There's only two of you.
I think no, because it just like depends on the car. One of the cars could have had a great start and then the other one was like behind it, but then at the end, like car A sped up to catch up to car B.
Just at the end, right? They only have to catch up at the very end.
Yes.
So that would challenge the idea that somewhere in the middle they had to be tied. Because so let me try and illustrate this. Let's all agree with this. Do both cars have the same average speed? Do they both cover the same distance in the same time? Yes?
Yes.
Okay, that we can all agree on. Yes? So if I were to try and like visually represent that, if we had, let's say, we'll do car A in blue. So car A is going to start, right? This is time, and this is distance, right? So they're going to start the race, and then, you know, after a certain amount of time, I don't know what it is, this car, whatever it does to travel, right, it's going to get to some point at the end and have covered the distance in that amount of time. And the other car is going to do some other trip, whatever, and they will both end together. Yes? So since both of those cars start and end at the same place and it takes them the same amount of time to go the same distance, then they both have the same secant line. Right? They both have the same secant line. Agree? Now, the mean value theorem says that for the blue car, there's some point in time, right? For the blue car, there's some point in time, C, I'll call it, I don't know, C for the blue car, CB, where that point I will be tangent to that purple dotted line, right? And the mean value theorem also says that for the green car, there's going to be some other C, not necessarily the same. I'll put it here for the green car. I should have done A and B. Sorry, let's do A and B. So for car A, right? And then for car B, we have some point where it's tangent as well, right? But the mean value theorem in no way is telling us that it has to have that the CA and the CB have to be the same, right? Just that we know that we're going to have it for each one is going to have one. What I'm asking you is this happening at the same point in time? So what Halle is saying is, think of this scenario where you have the car, one car that starts out really, really fast and gets to the end, and the other car that starts out really, really slow, but speeds up at the end like that. Is there a point in time where they're both going the same speed? In other words, is there a point in time where both of these, the tangent lines are parallel? Like, so you would have to somehow find in here a C somewhere in here where when you looked at both of them, they were parallel. Understand? This is still an open question. We could argue about this. People could state their case and they could try and figure it out, all right? There's only one way to do it, to get a final answer, and that's to do it mathematically precisely. All right, so I'm going to show you how to do it. Ready? And I've got 3 minutes, so I don't know how this is going to go. If you need to go at 2:40, you go. You can come back and watch this. All right, I'm going to finish this off. So the way I'm going to do this, nobody in here is going to think of. All right, this is just show you the way mathematicians think and the way that you could utilize something like the mean value theorem to answer something very, I guess this is very ambiguous. Like, we could argue all day long, right? We could argue all day. You could argue your case, someone else could argue their case, and you could go with what you believe. But at some point you have to have mathematics to actually get the answer. Like, what is it? It's one or the other. They either have a point in time where they're both going the same speed or they don't. So here we go. Here's how I'm gonna do it. I'm gonna call this function up here f of x. I'm gonna call this function down here g of x. Okay? Here's what I want to show. I want to show there is, and let's call the starting time A and the ending time B, okay? So I want to show there exists a C somewhere in between A and B such that they're going the same speed, which means that the derivative at C for the f function is equal to the derivative at C for the g function. Would you be satisfied if I could show you that that's true? That there's some point C in here where these two tangent lines are parallel. The tangent line to f and the tangent line to g, they're parallel to one another, which means they would be going the same speed there, right? Would you be satisfied with that? Okay, I'm gonna try and satisfy you now. So that's my goal. Okay, everyone, that's my goal, all right? I'm gonna try and prove that to you. So here's how I'm gonna do it. It's gonna blow your mind. I'm going to define a new function. This new function I'm gonna call capital N for new, because it's a new function. This new function, n of x, is going to be the f function minus the g function. The difference of the two. Now, why? Okay, just hang tight. After I've defined that, I want you to tell me what's n of a. What would happen if you plug a into both of these functions? F of a minus g of a. What would that be equal to? It's the difference between the two functions at a. So go to a. What's the difference between the two functions? Well, they're at the same place, aren't they? There's no difference between their positions in the very beginning. They started tied, didn't they? So the difference between those would be 0. What's n of b? So tell me what's happening at the end of the race.
0, 2.
0 as well, right? N of b is 0. Okay. Also, do you agree that n is continuous? All right, so look, the original function f and g, those were the cars driving down the road, right? Those should be continuous functions. It's not like the car's driving, it goes into some like wormhole and then comes back and appears in a different place down the track, right? I mean, these should be nice continuous paths. Y'all agree with that? When you subtract two continuous functions, you still have a continuous function. That's a property of continuous functions from earlier in the semester. So n is a continuous function, right? So I have n is continuous on the interval AB, and n of A equals n of B, which equals 0, which means if I graph the n function, I know that at A it's 0, at B it's 0, right? And whatever the graph does, it does, but I know that it starts, this is the n function, that it starts together, ends together. Right? Which means by Rolle's theorem, there's got to be a point somewhere in here, right? There's got to be somewhere, that's not a good position. There's got to be some point in here where this is true, right? Where there exists, by Rolle's, there is a C in the interval AB such that the derivative of n at that value C must be equal to what? 0, right? Y'all agree with that? But hold on, I got you. I've just proven it. You don't realize I have, but I have. Okay, I didn't mean to do that. Copy. But what is the left side of this really mean? So go back up and think about n. here was the definition of n, right? If I asked you to take the derivative of n, you would take derivative of this side and this side. When you take derivative of these two, you do them separately because there's subtraction between them, right? So isn't this really saying, this left side, isn't that really saying that f prime of c minus g prime of c must be 0? Add g prime of c to both sides. And you get this, don't you? QED, that's it. QED means I'm done. A little black box at the end means I've shown what I have tried to show you. You said you'd be satisfied if I showed you that, right? I just showed it to you. I just showed you that there is a point C where f prime equals g prime. Very strange, right? Very strange. Like, how would you ever think to come up with this difference of the two functions? But now that you've seen it, you can see how powerful just Rolle's theorem is in settling a question that we could sit here and argue about for weeks and weeks and weeks. No, it'll never happen. Yes, it will. No, it won't. So if two cars are racing, they start together, they end the race together. There's some point in time where they both look at the speedometer and they're going the same speed. And it happens somewhere in the race, not at the beginning and not at the end. It's somewhere in the middle. I can't tell you exactly where. I just know that it happens. It must happen. Okay. Do those homework problems. Also go back and maybe look at 4.1. Have a great day. See you Thursday. Okay.
Thank you. Bye.
Bye-bye. I'll be back here at 4.
Thank you, Professor.